The Counter-Strike economy is valued at nearly $8 billion. The assets traded have zero intrinsic value and no physical backing. The tech industry assumes an economy of this scale requires decentralized ledgers. These assets are not NFTs. They do not exist on a blockchain. The entire structure operates inside a strictly centralized relational database, owned and maintained entirely by Valve Corporation. This chart graphs the daily transaction volume on the Steam community market. Millions of operations are processed here every 24 hours. To understand how this economy actually functions, we have to deconstruct its engineering, starting with the mathematics that generate a single item. The value of these digital items depends on a system that enforces strict, unchanging parameters for every single transaction. Every weapon skin is a dynamically generated object, parameterized at the exact millisecond a player opens a digital crate. The first critical variable is the paint seed. It is an integer from 0 to 1,000 that dictates the X and Y offset, as well as the rotation of the weapon's texture map. Next is the float value. This is an IEEE 754 32-bit float ranging from 0.0 to 1.0, and it strictly dictates the item's visual degradation. The server-side random number generator places that float into predefined wear brackets. A skin has roughly a 3% chance of rolling factory new, compared to a 33% chance of landing in the field tested range. Valve overrides the 0.0 to 1.0 limit for specific items. Capping the minimum float at 0.14 prevents older weapons from generating with unnaturally clean textures. The database calculates a capped item's final wear state using a specific equation. The generated float is multiplied by the maximum float minus the minimum float plus the minimum float. Traditional game design creates assets manually. This parameterization generates trillions of unique, mathematically verifiable permutations from a single baseline texture file. High-entropy math creates strict digital scarcity. That scarcity forms the baseline of value for the entire $8 billion market. Generating an item is simple. Tracking 500 million of them as they move between user accounts requires complex database architecture. In 2017, Valve updated their API and permanently obfuscated the original Asset ID endpoint. Third-party trackers lost their direct line of sight on individual items. To bypass this, the community engineered a composite key. By concatenating an item's high-entropy, immutable properties, the float, paint seed, definition indexed, and paint index, they built a new identifier. Multiplying the 300 million usable floats by the 1,000 paint seeds and 1,000 skin types yields roughly 300 trillion possible combinations. This probability curve plots those permutations against the existing population of 500 million items. The math dictates that roughly 30 natural collisions will occur. A natural collision means two completely separate items are generated with the exact same 32-bit float and paint seed by pure statistical chance. The database also has to account for the duplication cheat. Historically, Steam support manually cloned scammed items, injecting unnatural, identical duplicates directly into the economy. When an external database encounters identical composite keys, it resolves the conflict by defaulting to the most recent inventory timestamp, effectively hiding the duplicate. Because identifiers are composite, an item's verifiable history relies entirely on continuous, uninterrupted visibility within the database. Observing an item is a passive action. Executing a secure transfer of ownership between two users requires an entirely different set of protocols. Valve handles this through the Steam Inventory Service, built entirely around the untrusted client architecture principle. Local machines cannot dictate state changes. If a client had authority, attackers could capture keys or inject memory to assign themselves any item they wanted. This architecture diagram maps the restriction. The client can only issue a trigger item drop request. The trusted server holds absolute authority to validate that request and execute the state change directly to the core database. That server validation enforces an automated economic sink. A rigid 15% fee, 10% to the publisher, 5% to Steam, is deducted from every transaction. These database commits are atomic. Wallet funds and item ownership swap simultaneously. There are no pending states, and zero capability for traditional financial chargebacks. Economic trust here relies on the absolute, unyielding dictatorship of the trusted server's validation rules. The external pressure on this database is immense, driven heavily by third-party markets operating fleets of automated trading bots. This concurrent processing creates race conditions, unpredictable behavior that occurs when multiple operations compete to execute out of sequence. This timeline illustrates a specific race condition. Two separate automated bots fetch the exact same real-time data, simultaneously attempting to execute a buy order on a single, mispriced high-value item. If network latency allows a buy order or a stop loss to process based on outdated state data, the database risks immediate corruption. To prevent this, the server relies on precise timestamping and strict chronological ordering. The queue accepts the first packet to arrive and forcibly rejects the second. Secondary load balancing mechanisms restrict traffic further. Aggressive API rate limiting bottlenecks automated requests to a maximum of 1 per second per bot. For accounts lacking the SteamGuard mobile authenticator, the server mandates a strict 7 to 15-day trade hold. Players view these holds as security inconveniences. In reality, they are strictly engineered synchronization and state protection limits for a highly contested database. The entire Counter-Strike economy functions on the journey from the generation of an IEEE 754 float to the atomic commits of the Steamworks API. For a decade, the broader tech industry has spent billions trying to build functional economies using decentralized ledgers. The skin's visual aesthetic functions as the front-end user interface for its relational database entry. Valve built an $8 billion economy using standard, battle-tested technologies, centralized servers, floating-point math, and chronological queuing. In digital economies, the absolute certainty of the database row creates, sustains, and protects the item's value.